So right out of the gate, I want to talk about the specs of this board. The top speed is 18 miles per hour, and I tested this speed while on the board. The max range is about 6 miles, however this heavily depends on the battery configuration, and of course, if you charge the batteries properly. In this board, I'm running 6 cells in series from 2 different batteries, and the total cost for this entire board is under $400. Alright, so I'm about to head off to the forest preserve, and I'm going to be testing the range of the board. Now, I have done previous testing, but those tests were inconclusive, and I just want to get better results. I'm also going to be using an app called Run Tracker, and this app will just basically track my speed and my distance and my pace. It's for running, but you know, the app can't tell the difference between running and me going 18 miles per hour on a board, right? Well, after 5 continuous miles, the board has finally died. It was getting very close to 6 miles, so I'll probably just call it 6 miles. And I also did a lot of other various shooting with the board, and so that meant going back and forth along like a straight path and not just, you know, going the full range right away, because I was doing various shoots. Anyway, so now I'm in the situation where I have to push my board all the way back to my car, which is 5 to 6 miles in the other direction. Since the board is heavy, I just have to push off a few times and the board just keeps on going. Like once I have my momentum, it just keeps on going because of inertia, you know? Alright, so these are the 2 batteries after my ride, and I'm going to be testing the voltages of each cell. Now I could do this on the charger, but I trust my multimeter a little bit more. Alright, 3.5 first cell. That's actually pretty good. 3.6, okay. I like what I'm seeing right now. 3.6, okay. See, the lowest voltage that you should ever get your cell to in a LiPo battery is 3.3 volts. And when it gets to 3.3 volts, it's fully discharged. And going any lower than that, you risk puffing up the battery and completely destroying the battery. And I've done that before. So what I actually did in this board, I actually programmed this guy to monitor not the individual cells. You can't actually monitor the individual cells with this, but you can monitor the total voltage of these 2 batteries combined, and then with a little bit of calculations you can determine what each individual cell voltage will be at a certain total voltage. And that's what I just programmed into this VESC controller, and I told it basically once it gets to a certain total voltage, then it should limit the amount of power that's going into the motor. And this way, it not only protects your batteries and cells of your batteries, but I think it's also helpful because it gives you a low voltage warning, and it just helps to preserve your batteries so you don't over discharge them. Alright, 3.4 volts, 3.6 volts on the second cell, and 3.6 volts on the third cell. Wow! And I think honestly, even though these batteries are not fully discharged, well, because you can still discharge the cells closer to 3.3 volts, and you would get a longer runtime. You would get a longer range, and you could use this board for a longer period of time. However, you are risking damaging the batteries and lowering their life expectancy. You could get longer ranges with your board if you sacrifice your cell voltages and just discharge them more, but like I said, it's risky. So I'm very glad I programmed this in the way that I did, because it does save your batteries. When you approach that voltage limit that you program into this controller, well, the controller doesn't immediately cut off the voltage, it just limits the amount of power going into here. So you start to try to speed up on the controller, but what ends up happening, it still stays the same speed, or you get slowed down over time. And like I said, it just limits the power. It doesn't cut it off completely, but it just limits it. And it gives you a nice warning in that sense that your batteries are low. All right, so when it comes to charging your batteries, there's a lot more to it than meets the eye. So when I first started doing this, I bought this B6 compact charger, and it was actually decent for a while. It charged up my batteries a couple times, and then unfortunately something broke inside of it. And I'm like, okay, well, this is actually pretty cheap, so I'm just gonna buy another one. So I bought another one, and same thing, it charged up my batteries a couple times, and then something broke inside of it. I don't know what it was. So I'm like, you know, it's still fairly cheap, so I'm gonna buy a third one. Now, third time's the charm, right? Wrong. Actually, maybe so, because only half of it broke. See, like, it's still functional, but, you know, half of these ports don't work and half of them do, so honestly, I don't know. This charger is too unreliable. And because it's so cheap, you honestly get what you pay for. So you get my point. Do not spend your money on this product. So that's when I bought this, the Imax B6 balancing charger. And it has an LCD display, and it gives you so much information. It can charge a bunch of different batteries. And honestly, I can't recommend this enough. It's reliable, and it still has lasted throughout all the different batteries and charges that I put it through. Now, there's another thing to consider, because being the person that I am, I'd like to save as much money as possible. And I'm like, see, I have 3-cell batteries, and I have 2 of them, right? So if I connect those 2 3-cell batteries together, that makes a 6-cell battery, one big battery, right? Now this charger can charge 6-cell batteries. So I'm thinking, maybe I just buy a connector, right? Well, I did buy some connectors, and let me tell you, they suck. Do you see how charred they are? And by the way, I had to replace this socket, this connector, because it was completely just like melted off. It's just ridiculous. I don't care how careful you think you are, you will mess up connecting these connectors to this and connecting both of your batteries to these connectors. You will mess up somewhere along the way, because if you're in a rush or you're distracted, well, good luck. I've blown up a battery just by connecting this stuff wrong. And believe me, I thought I was careful too. I was extremely careful with connecting everything up, but even being that careful, it's just not enough. Just keep it simple, and if you're working with 2 batteries, I recommend buying 2 of these, and just stick with 1 battery to 1 charger, and that's it. As you can see, I like making things complicated for myself. So the first thing that you should know when connecting your battery over to the charger is there is actually a procedure to doing this. So to prevent any sparks or arcing when you connect the battery over to the charger, you have to connect the big leads first, and then you connect the smaller leads. So these are the cables that I made to connect the battery over to the charger. And if you could hear that, there was a spark as soon as I connected these 2 leads, these 2 DIN connections. But now I can safely connect my smaller wires over. So I already set up the charger for lithium polymer batteries, and I set it up for a balancing charge. I always do balancing charge. Now to change the other settings, I just hit enter or start. Now it's going to start blinking, and then you can cycle through all the options. So 3-cell, that's what this battery is. It's a 3-cell. Press it again to cycle through. 5,000 milliamp hours. This battery is a 5,000 milliamp hour battery, so I'm just going to keep going. And yes, that's what we want. So now it is charging at half an amp. Now you could charge this at 1 amp, for example. That would be fine too, but generally speaking, the lower the amps that you charge the battery in, the better, but up to a point. You know, you don't want it to charge too slow. I always like charging my batteries as slowly as possible, so half an amp is perfect for me. But if you want a slightly faster charge, go up to 1 amp. But yeah, I usually never go above 1 amp. I like charging my batteries slowly, just to make sure there's no damage to them. And if you want, you can cycle through all the cells and just watch all the cells individually, which is really nice, actually. Oh yeah, and when you buy these chargers, they don't come with a power supply. So if you're wondering what I'm using to power it, well, it's this. It's a 14-volt DC 3-amp power supply, and it actually works really well. I think this used to power either a monitor or a laptop, but I repurposed this to connect over to the charger. So this is the data that I got from the tracker app, and at least for the first 2 miles, I was stopping and going frequently and going back and forth along the trail just to get some shots of the board, to record some shots for the board. So that's why the first 2 miles took me such a long time to complete in this app. So I'm not going to count those 2 first miles, but I'm going to go from mile 3 to mile 6. Now I also calculated the speed for each mile that I completed, and you can see for the first 2 miles that my speed was pretty slow, and so I was wasting a bunch of time over here. But after mile 3, I continued at a regular pace, and you can see that in the data. The highest speed I went to was 7.5 miles per hour, and actually that feels very fast on a board that small. I didn't even push the board to top speed, but it was still very fun to ride. And the point of this test was not to go full speed. The point of this test was to see the range of this thing, and so I knew I had to pace myself. I think this was a good test, but I also think I can do better than this. But because of the first 2 miles, the results are a little bit skewed. So I'm going to test this one more time, and I think I can do a little bit better than these results. So I did the test again, and this time I did 5 miles in about 35 minutes. And the app is telling me that my average pace was 1 mile per 7 minutes. So if I do 60 divided by 7 minutes, that's roughly 8.5 miles per hour that I was going at. That's a pretty decent running pace, don't you think? Now the board still had some juice left over at 5 miles, but I decided to stop it at 5 miles just because the board was no longer fun to ride. You could feel that the board wanted to accelerate, but it wouldn't go fast. It was, like I said, not fun to ride. And then when I got home, I recorded each individual voltage for each cell in the batteries, and this is what I got. You can see that one cell on the second battery is really low. It's to 3.3 volts, which is fully discharged. You do not want a cell to discharge more than 3.3 volts. But you can also notice that all the other cells still have a bunch of charge left in them. They can still be discharged. So really, this one cell is holding all of these other cells back. Now, this low voltage in this one cell can be caused by a faulty cell in a battery, or it can be caused by the charger improperly balancing the cells when it charges the battery. Now, I don't think this is due to the charger being faulty. I love the Imax B6 charger, but when I opened it up, I noticed those some components were charred, and I think it was just my fault because when I decided to charge 2 batteries at once, and I think I might have made some wrong connections, and so when I tried plugging in that battery into the charger, then something inside just broke. And that's purely because of my fault. Nothing to do with the charger itself. The charger itself is a great product. So my point is, if this cell wasn't as low, then I could have gotten way more than 5 miles out of the board. So hopefully from this you can see that it's very important to charge your batteries right and also discharge them right. Now these are the type of batteries that I use in my board. They're the ZIPPY 3-cell 5000 milliamp batteries, and they're actually a fairly good price, and so you're getting a lot of bang for your buck when you buy these batteries. Now I know there are cheaper batteries that are exactly like these, which have also 5000 milliamps and also have 3 cells. But even though they're cheaper, they tend to usually not come with bullet connections. And that's why I like these batteries so much, because they come with these bullet connectors. And these bullet connectors are actually pretty useful, because if you want to use 2 of these 3-cell batteries in series, well, it's really easy with these bullet connectors. You can just connect up these batteries like so, and there you go. You have both of your batteries connected and ready to connect over to your VESC controller. Now, once these batteries are hooked up and are ready to be used, what I do is I get this cable out. Now, I made this cable specifically to use with my board and also for charging, so it has dual purpose. So this DIN connector side goes over to the charger when you're charging these batteries, but it also connects over to the VESC controller that controls the power going to the motor. On the other side, I have bullet connectors, and when this is all ready and charged up, you just connect it like so, and you're all set. You're all ready to go. You can put these batteries in your case under the board, and you can plug this right into the controller, the VESC controller, and you can be on your way. This is done for convenience, and I think this is a pretty elegant solution. Now, you could argue, why use 2 batteries when you can easily purchase a 6-cell battery and just replace both these batteries with one giant one? Well, space becomes an issue. So this is the approximate thickness of one battery, and a 6-cell battery is going to be approximately double this thickness, and so you can only imagine how thick that single battery is going to be. And then if we put both of these batteries, or try to put them into this case. Now let me see if I can fit all of this in here. And yeah, there you go. Yeah, so I mean, a 6-cell battery I guess would fit in this container, but you're pushing it. I mean, yeah, this is secured and, you know, both batteries on top of each other fit, but I wouldn't secure the batteries in this way. I like giving the batteries legroom. I like giving them space, because you got to consider that when the batteries are discharging, they're going to get warm. It's better to have a lot of space around them so they have a lot of surface area to cool off when they're being discharged. I already have Velcro straps to secure everything down pretty tightly, and that works just fine. So as long as everything is secured down tightly inside and it doesn't rattle around everywhere, I'm not too concerned about stuffing the ever-living hell out of this box to make sure that, you know, nothing wiggles in there. Now this switch over here is actually worth talking about too. Now this is a 4 amp switch rated at 125 volts. And it does a great job when it comes to switching the power from the batteries to the controller. Now I've had a different switch on here, and that first switch that I put on actually degraded over time. Those contacts of the switch were getting destroyed because when you switch on the power from the batteries to go into the controller, well, you're creating a spark, and that spark or arcing in the switch can degrade those contacts over time, and so you need a beefy switch. And hopefully here you can see how the switch is wired up. It just intercepts the power that's coming into the controller. That's all it's there for. Now this container itself is a snapware container, and the dimensions of this are approximately 5.5 inches long by 7 3/4 inch long, and the depth is approximately 2 inches. Now to secure this container to the board, I decided to use 4 screws on each corner of the container and really large wide washers, and that just makes it really stiff and makes sure that the container is held down properly. Now notice how I installed this container in the middle of the board. Now in this particular situation, I think that was a mistake on my part. What I should have done is installed this container a little bit forward, a little bit on the front end of this board. And the reason behind that is so it would be easier for me to carry the board. Because since this container is in the middle of the board, then it just makes it really awkward to hold on to if I'm carrying it. But also take into account that this board is very stiff and thick. It doesn't want to flex at all, and it's kind of a short board. So if this board experiences any vibrations, well, there's no flexibility, so all of that energy is going to be felt by you, the rider. Now, whether or not your board flexes a lot can also determine where you place your container or where you attach your container. Because if your board is very stiff, then you don't have to worry too much about the placement or installation of this container. But if your board does flex a lot, then the most amount of flex you're going to get is in the middle section. And you want the compartments where you hold the battery and various other things to not flex, and to not risk those screws that are holding the compartments down to get loose. But not only that, over time, those holes that you created from the screws that are used to mount your containers with, well, those could actually ruin the board over time, create larger and larger cracks because of the flexing. So you have to really think about where you make your holes and where you place your compartment. So these are the type of bearings I'm using in the board right now. And these bearings came with the wheels. Now, even though they're cheap and came with the wheels, they're not bad bearings. And generally for those boards that are not powered, you want good bearings in them. You want the bearings to spin as long as possible so you can get the most out of every push when you're on the board, right? But when you're talking about an electric longboard that's powered by a motor, I think cheap bearings are okay. There's really no need to spend more on bearings. Now, if you still want to spend some extra money on good quality bearings, but not overspend, not spend too much, I do recommend the Bones Reds bearings. I actually use them in my own skateboards that are not electric, that are not powered, and they work great. They last a long time and they're pretty cheap, so you know, you won't be spending a lot for a good ride. They also include these weird spacers that go in the wheel itself, and it goes in between both of those bearings, and it just causes more friction, so I honestly don't use them at all. So these wheels are pretty much the biggest you can get, and I suggest if you're making this electric longboard, then you go straight for the 90mm wheels. You will save a lot of time and energy by just going straight with these wheels. I know they're big and I know they're heavy, but it makes your life a lot easier, especially on the road when riding. Bigger wheels are easier to get over cracks with, and you don't have to worry about what's on the ground as much. Not only that, but because the wheels are large, obviously they're going to lift the whole board up a little bit higher. That gives you just more clearance for things that you want to put under your board, like a compartment for the batteries, you know? And here's the biggest reason why you should go straight for these wheels. It's because they have holes in them. Now, when you're connecting the motor to the wheel, you're going to need a bracket that goes on the wheel itself. You're going to need bolts that go through these holes and mount on the actual wheel, so the pulley can actually have something to attach to and drive the wheel, right? Now, with the 90mm wheels, I found that it's really easy to get, you know, those holes that you are looking for to mount that bracket in, and it's really simple. But I have also tried to make my own holes in smaller wheels, and let me tell you that it's not going to work out. It just doesn't work. All right, so first I'm going to put on a washer, and now the wheel, and then another washer, and then finally the nut. Now, to make sure that the wheel is spinning as freely as possible, you have to make sure that it's actually fairly bit loose. Not as loose as this. You don't want it this loose, so I'm going to tighten it and see if the wheel is loose. And it's not loose, but just from experience, I don't like the way this is spinning. It's actually being slowed down a lot by how tight I put on the nut. So I'm going to unscrew this nut a little bit. Oh, and now I can feel that the wheel moves from side to side just a little bit, just a very tiny bit. And now, look at the improvement that we made to how this wheel spins. Now we have successfully installed the wheel. And these trucks are called Paris V2 trucks. They're 180 millimeters, which is, I think, standard. And overall, they're great trucks. Whether or not you're using them for an electric skateboard, they're just overall great trucks for longboards. I found that these trucks are reliable and durable, which is essential for electric skateboards. And they're also fairly cheap, too. As soon as I turn the board over, I notice just how many washers like these I have on the board. If you're wondering the dimensions of this washer, here I'll just do it really quickly. It looks like these washers are 1.5 inches in diameter, and it looks like maybe a 1/4 inch of a hole in the center. I just do this from experience just because I know if the bolts get tightened down too hard, they can sink into the wood and start to create a crack, which is what I don't want happening, especially on a board like this that's powered by a motor. But what I really want to talk about is the type or style of board that I'm using. I'm not exactly sure what this type of style is called, but I know that a lot of boards that are labeled twin longboards or drop-through boards have this type of style to them. And I'm a really big fan of this just because it provides a lot of room for the wheels, and because, you know, the wheels are big, they're 90 millimeters, you want as much space for those wheels, and it makes sure that when you're turning on the board that the wheel doesn't hit the underside of your deck. And if it does, well, that's called wheel bite. And if that happens on an electric skateboard when you're going really fast, well, that can cause you to fly off. Now, when you're buying motors for your board, you might be wondering, do I need 2 motors? And my answer would be, well, it depends. It depends on your budget. If you want to save the most money, I would go with a lower kV rated motor. And you're saving money when you're buying a single lower rated kV motor just because it's one big motor that can handle a lot of torque and give you both the power and the speed that you want, even despite it being hard to mount on the board itself. I don't recommend that you go lower than 190 kV because this is a 190 kV motor, and well, I'm pushing the limit of what I can attach to this bracket over here. I mean, just look how much clearance I have over here. And you can see that the motor is mounted a little bit below the truck line, but if the motor was mounted any bit higher, then it would be level with it. So what I'm saying is one motor is more than enough if you pick the right motor. So if you're going for just a one motor setup, then going for a lower kV motor, which means a bigger motor, is the best course of action, is the best choice here. And if you're going for a one motor setup, then you only have to buy one speed controller for the motor. But if you're going for 2 motors, well, you're going to have to buy maybe more batteries and definitely more than one speed controller to control the motor. Unless you buy one speed controller for both motors that's beefy enough to handle all the power that the motors will require. So if you're going for a 2 motor setup, go for a higher rated kV motor, which will be smaller and provide less torque, but it will be easier to mount to your wheels. And since you have 2 of these motors, well, then torque shouldn't be much of an issue. But of course, buying 2 motors and possibly 2 speed controllers, you could buy one and run both motors in parallel, but you would have to buy a more expensive, beefier speed controller for the motors, so just keep that in mind. And all of this would probably just equal more money out of your pocket. So if you want to save the most amount of money, I would just suggest going for the single motor setup. But if you can spend a little bit more and want an easier time mounting the motors to the wheels, then you could go for a double motor setup. One choice is not necessarily better than the other, it's just what you prefer and your budget, basically. Now I want to show you something useful. Watch this line that I put on the wheel. Now it's going in one direction, right? But what if I didn't want the wheel to go in that direction? What if that was the wrong direction, right? How do you change that? There are 3 wires that go to the motor, and all you have to do is select 2 of them, and it can be any 2, and just switch them. So I switched these around, and now when I try to turn the wheel, it turns in the other way, other direction. Now when it comes to the clearance underneath your board, well, having too much clearance is better than having too little, and I say that from experience. Now back when I was using smaller wheels and different trucks, I had a much lower board, and therefore the motor was much lower to the ground. And I was in a situation where I was going really fast, and I didn't have time to avoid going over some sticks. Now a stick went right underneath my board and got lodged between the motor and the ground, and it stopped me from a very high speed. It almost knocked me off my board. A good rule of thumb to follow is that your motor should be level or below your truck's, and that means your motor should be closer to your board deck than the ground. What you could also do is mount the motor differently. You can mount the motor back here, and then when any rocks or sticks come by, they hit the truck first rather than the motor first. But when the motor is mounted over here, I found personally it's just more annoying because I like to use my foot and kick this board up on the edge, and it just hits the motor. The motor is being scraped along the ground, and I just don't want that to happen. So I just put it in front here rather than in the back. But as long as the motor is above the truck line, then you should be fine. You don't have to really worry about where to mount it. Just worry about it being level or above this truck line. So I'm putting more pressure on the belt, and when the belt is really tight on the motor shaft, you can see that the entire motor just wants to compress more on one side. And you can see that gap getting smaller right there. And if your belt on the motor shaft is way too tight, the motor will constantly run like this, and it will just stress out the bearings inside the motor to the point where they can fail prematurely. So as you can see, my belt is really loose, and I actually ride the skateboard this way. But this is not intentional. I do want to make this belt a little bit tighter because this is way too loose. But what ends up happening, even though I try my best to screw in the motor as tightly as I possibly can to the bracket here, it just keeps sliding toward the wheel, and it just makes this belt looser and looser. But what's surprising is that even though it's this loose, it still performs really great. Because I'm using large teeth on the pulleys in the belt, I can get away with having the belt this loose, even though you really shouldn't have it this loose in the first place. But you will have to experiment with the tension on the belt and see what you can get away with. Too much tension and you get a lot of unnecessary friction that can cause premature bearing destruction in the motor. Too little, and of course you won't be able to accelerate or brake properly. Now one time when I was riding this board down a street, I happened to notice a scraping or rattling noise coming from the motor. Now because I was coming back home at this time, I decided that I would ignore that noise until I got back home and I would check it out then. But in a couple of minutes, that scraping and rattling noise got louder and louder because, you know, I was going fast on this board, and then all of a sudden the board breaks by itself. And what happened was that the bearing inside of the motor just disintegrated to the point where it was stopping the motor from turning, and it stopped the entire board. I almost flew off my board going at a high speed. So of course I got frustrated and I thought that I needed to buy a new motor, and I almost did buy a new motor, but thankfully I realized that these bearings have numbers on them, and this bearing in particular has 6800Z on it. So I just simply looked that up online, and it turns out that these bearings are really cheap. And normally I don't see videos of where people go in depth on topics like these, because usually if, you know, a motor breaks for any reason, then you get a new motor. But this is valuable information, because if your bearings in your motor break, well, you would rather spend less than $5 replacing those bearings than up to hundreds of dollars replacing the motor, right? Of course, what caused the bearing to disintegrate in the first place was the belt that I tensioned on it way too tightly. And that belt tension is directly related to how much stress these bearings experience. So you do have to be careful. You might notice that the motor shaft is flat on one end, and I actually did that. I filed down a flat surface on this motor shaft because I had a problem where when I put this pulley on, it slipped way too much. So after making a flat spot on the motor shaft, I just aligned the screw on the pulley with that flat spot, and when I tightened it down, it didn't move at all. During accelerating and braking, it didn't budge at all. So it's really beneficial for you to make a flat spot on your motor shaft just to keep this pulley in place and prevent it from slipping. So let's talk about the pulleys and the belt that I use. So for starters, let's just quickly go over what these numbers mean on the belt, and this will help you decide what kind of belt you need. So this is a 300-5M belt. Now the 300 stands for 300 millimeters, and I can prove that to you really quickly by measuring this on a ruler. So you can see one length of it is 15 centimeters, and of course this is a belt, so we double that 15 centimeters, and that gives us 30 centimeters. Now there's 10 millimeters in a centimeter, so 30 times 10, that's 300, and that's where this 300 comes from. That's 300 millimeters for the total length of the belt. Now for my specific motor mount bracket, I found that a 300 millimeter belt is actually perfect, but this will vary. This will vary on the pulleys you decide to use, and it will also vary on the motor that you decide to use. And it will also depend on how long your bracket is too, so you just have to calculate these things yourself. Now the 5M part of this belt refers to the pitch of the teeth in the belt. I'm not entirely sure if that's correct, if it deals with just the pitch or like a combination of things that actually represents the size of the tooth, but you can look at that number as basically the size of the tooth. And that number is important because you obviously want the teeth on the belt to mesh with the pulleys that you choose. And so when you start searching for pulleys, you have to make sure to type that number in. So obviously when you're buying pulleys, you should get a 5M pulley to mesh with your 5M belt, right? Now this small pulley is a 20 tooth pulley, and this larger one has 36 teeth. So what that basically means is that when the motor turns one full revolution, the wheel will turn about halfway. Now just for fun, let's calculate the theoretical maximum speed of this 190 kV motor. So we start off with 190 kV multiplied by 25.2 volts. Now this 25.2 volts comes from multiplying the maximum cell voltage, the maximum individual cell voltage, which is 4.2 volts, multiplied by the total amount of cells that we are using to power the board. And so this is your total voltage, and when you multiply all this, you get your RPM. Now keep in mind this calculation is made without any load on the motor itself, and a kV rating for a motor also implies that. Anyway, we have the revolutions per minute of the motor, but what I want to see is miles per hour. So that's why we multiply the RPM by 60 to get the revolutions per hour. And then we don't have to worry about time anymore, we have to worry about distance. So then we get the circumference of the 90 millimeter wheels that we have, and we get 282 millimeters per revolution. Now I just converted that value into centimeters per revolution, and then we multiply that distance per revolution by the total amount of revolutions in an hour to get our total distance covered in an hour in centimeters. And then of course we have to divide this large number by how many centimeters are in a mile, and then we get 50 miles per hour. Now this is the theoretical top speed of the motor itself. This is not the top speed of the wheel, because remember, we are dealing with two different pulleys that have two different amounts of teeth. We just simply multiply the 50 miles per hour by that ratio, and then we get 28 miles per hour. That's the theoretical top speed of the board coming from the wheel itself. With no load on the wheel should spin about 28 miles per hour. But of course that's not a realistic number because we have to factor in friction and of course drag when you're going at high speeds and other inefficiencies in this system. And then so what you end up with is 18 miles per hour. And this 18 miles per hour I actually recorded and I measured while on the board. Now this is what the motor bracket looks like, and you can probably already tell that because these Paris trucks were a little bit too big, I had to grind down some metal in order for this bracket to fit. Now the most frustrating thing about this bracket for me personally was the screws. Now when you get the kit, it comes with the screws, but the kit doesn't list what the screws are, what they're called. And this really frustrated me because what happens if you lose a screw or if one is missing from the kit when you receive it? I don't want to spend more money and just buy a new kit just to get those screws, so I had to literally spend a few hours searching for this stupid screw. So these screws are called Grub screws, and they usually come with pointed tips. Make sure to also get Loctite when working with grub screws. It's very useful because once those grub screws start experiencing vibrations when you start riding your board, they're going to get loose. Now pointed tips are okay and they're pretty much the standard, but what I found helps the most is actually flattening these tips to make them, well, flatter. I found through experience that you don't really want these grub screws digging into the metal that much. What you want is more surface area, so what would be better to do is just to file down these tips just a little bit. Maybe someone who knows more about grub screws than me can help me answer the question of whether or not you want a pointed or a more flatter tip depending on the application, because I'm actually very curious. I'm not sure if a pointed or a flatter tip would work better or equally as well, or you know, maybe depending on the situation, of course. All right, so let's talk about this controller and the receiver. So when I bought this was literally called a mini remote controller with receiver, and in parentheses it was 2.4 gigahertz. So this has no branding, and it's literally just a cheap Chinese controller. That's all I can say about it. But honestly, the only thing I cared about when buying this controller is if it would be comfortable to hold, and it is. It really is smooth and comfortable to hold, which was one of the biggest reasons I bought this. And it may look cheap, but the potentiometer on this controller feels really nice. But the sensitivity of this is adjustable in the electronic speed controller that you buy too. Now the button down here turns the controller on, and when it's blinking like that, it means it's ready to pair. And you have a button down here and a button right here and a switch right over here to change the functionality of the remote. But personally, I never had to use the extra functionality that this remote control provides. Now the cool thing about this receiver that it comes with is that it has multiple channels. So it turns out that channel 2 is used as an expandable switch that could, for example, turn on and off a light on your board. Channel 2 is controllable from the remote, and in order to trigger channel 2, you need to hold the respective button for about 3 seconds. Channel 1 is the only channel with pulse width modulation, and in order to use this controller with two electronic speed controllers, you will need a cable splitter on channel 1 to run those signals in parallel. I don't have much to say about this VESC controller, but it can handle 50 amps and it can handle up to 12 cells, and as long as your motor can handle what you're putting through this guy, well, it should be just fine. Oh, and good thing I remembered to say this, because I don't know about other speed controllers, but this one in particular, I know can drive both motors that have sensors in them, like Hall effect sensors and so on, and also can drive motors without sensors. And actually I'm using a motor right now that doesn't have any sensors, and so that's important to consider too. If your motor has sensors or doesn't have sensors, and if your electronic speed controller, your VESC, can accommodate for that. So when you're connecting your VESC to your computer, you also need to power it with a battery. And I would also advise to connect your remote over to the VESC as well. So once you have your VESC connected over to your computer, you can start up this BLDC tool, this program, and on the top right here you can attempt to connect to your electronic speed controller. Now once you have it connected, on the bottom left here you can see read configuration. If you press this button, then that will just give you all of the numerical values of every single option on the page. And if you decide to change anything, you want to make sure to click write configuration. Now honestly, there are a lot of options in this program. There are so many things that I could talk about in this program, but I don't think I'm going to explain it fairly well. I don't think I'm going to do it justice, so I'm going to link two good videos on this program alone that you can look at, and it will tell you pretty much everything you need to know about configuring your board. I will also make sure to link the download for this program too in the description. But for now, I'm just going to show you what values I have in my setup, in my configuration, and you can pause the video as necessary. So I guess the last thing to talk about is, would I make any modifications or changes to this board? And the answer is yes, I do want to make modifications to this board, but it's going to take some time because I want to make a bigger battery. I want to make my own lithium-ion battery rather than rely on the lithium polymer batteries that I'm using now in the board. I don't have enough batteries right now to make a lithium-ion battery pack, but as soon as I find more of these batteries and make a spot welder to join all of these together, then I'll make sure to put out a video about that, because I'm curious how much range I can get out of these batteries. Now obviously, with building a new and better battery pack, I'm going to need to change where I place the compartment. So what I'm thinking of doing is making a compartment here that's dedicated to all the electronics of the board, and then a compartment at the very front that's going to be the actual battery pack. And that way it makes space in the middle of the board to basically carry it if I need to. I really like the 6-cell configuration that I have now, so I don't think I'll change the amount of cells that I'm using. I think I'll just put more batteries in parallel to increase the milliamp hour rating, and by increasing the total capacity of the battery pack, hopefully I'll get more range out of this board. Another thing that I want to change is making this motor mount a little bit more permanent. Now I'm thinking of maybe welding this together, but I believe these two plates are aluminum, and I simply have no equipment that can weld aluminum. However, I did do some research to see if it's even possible to weld aluminum with stick welding, and it kind of turns out it could be possible, so maybe I'll try something in that direction, but I'm really not sure yet. Another thing that I could try doing is modifying this bracket in such a way where it would be less susceptible to vibrations, would be less likely to move. Because a constant problem with this bracket is that it becomes loose over a certain period of time. No matter how much Loctite I use and no matter how tightly I screw in those grub screws, it always gets loose after a certain period of time. Another problem that's really annoying is that when I attach the motor to the bracket and I try braking or accelerating, what usually happens is the motor just over time starts to slide up the bracket like this, which of course loosens the belt, which makes it slip more and it makes it harder to accelerate properly. But this should be an easy fix because all I really have to do is cut out a piece of metal to fit in the slot and basically block the screws that are attaching the motor to the bracket from sliding up any further. So I know I may have missed some things, and if I did and you have questions, go ahead and ask them in the comments and I'll try my best to answer them. Now I know there's better setups for an electric skateboard, but if you want the lowest cost skateboard and still have a bunch of fun, then I think this is a viable option because, you know, money doesn't grow on trees, and I'm not trying to make you spend more than you actually have to. I made most of these decisions based off of price and budget. So for an electric skateboard that can go up to 18 miles per hour and up to 6 miles in range, this is not that bad at all, and especially because you have loads of options of improving this. So in summary, building an electric skateboard doesn't have to be complicated, and hopefully I explained things in a clear and comprehensible way so, you know, you can build your own and not have to spend a lot. Anyway, as always, thanks for watching, hope you learned something, and I'll see you in the next one.